All right, for lesson 13, we're taking a look a little bit more at the graphs of linear equations in two variables. And again, you're going to need some graph paper. So in your journal, the last lesson we saw that the solutions of linear equations in two variables can be plotted on a coordinate plane as points. So the collection of all points x, y in the coordinate plane, so that each xy is a solution of ax plus by equals c, is called the graph of ax plus by equals c. So do you think it is possible to plot all the solutions on a linear equation, or from a linear equation, on a coordinate plane? Well, it is not possible. There is an infinite number of values we can use to fix one of the variables. For that reason, we cannot draw the graph of a linear equation. What we can do is plot a few points of an equation and make predictions about what the graph should look like. So let's find 5 solutions to the linear equation x plus y equals 6 and plot the points on a coordinate plane and name a solution. So let's look at an example. Let's say we've picked these 5 points for x. That would be 0, 1, 2, 3, and 4, which means then our y, in order to make the solution true, would have to be 6, 5, 4, 3, and 2, respectively. So the graph of these points would look something like this. These points look like they are in a straight line. They seem to have a definite pattern to it. So can you predict the shape of the graph of this linear equation based on just these 5 points we have so far? Well, it looks like the points lie on a line. So at this point, you're correct. It does look like the graph of the equation is a line, but for all we know, there could be some curved parts between some of these points. For all we know, the graph of x plus y equals 6 could be the following curve. Notice that this curve passes through all of the selected 5 points. And here you go. So here are points that look like a neat line. However, the graph could look something like this, where it goes through all 5 of the points, but this is obviously not a line. So the only thing we can do at this point is find more solutions that would show what the graph looks like between these existing points. That means we'll have to look at some points with coordinates that are not that are fractions and not whole numbers. So name a solution that will plot as a point between the points we already have on the graph. We're going to add to our XY table, and a sample solution is provided. So picking some other points, such as 1/2, 1.5, 2.5, 3.5, and 4.5, will provide these other solutions for y: 5.5, 4.5, 3.5, 2.5, and 1.5. So now we're going to add these points of the graph of x plus y equals 6 to our coordinate plane. Well, they still look like they fall in line. Are you convinced that the graph of a linear equation, x plus y equals 6, is still a line? Well, hopefully you said you shouldn't be, because again, what if the graph looks like this? We've kind of zoomed in, but what if still there is a curved line that connects all of these points, but it's still not a line? So it's time to find more solutions. This time we will need to come up with solutions where the x value is negative or the y value is negative. So we've added more. We have -1, -2, -3, And then we also have some solutions which y is negative. In this case, -1 and -2 for y. So now we have 15 solutions to the equation x plus y equals 6. Are you convinced that the graph of this equation is a line? Here we have these plotted again. Well, hopefully you said that you are still unsure. Even though it looks like the graph is forming a line, there is still a possibility for a curve between some of the existing points. Based on the look on the graph, does the point 17/3, 1/3 belong on the graph of the linear equation x plus y equals 6? Why or why not? Well, it looks like 17/3 and 1/3 should be on the graph of the linear equation because it looks like the point would follow the pattern of the rest of the points. That means being on the line. So just by looking at the graph, we cannot be sure. We can predict that this point is on the graph of x plus y equals 6 because it looks like it should be. But how can we, or what can we do to find out for sure? Well, since each point on the graph represents a solution to the equation, and if 17/3 plus 1/3 is equal to 6, which it is, then we can say for sure that the solution 17/3, 1/3 is a point on the graph of x plus y equals 6. So just by looking at the graph, would you say that -2 and 3/7, 4 is a point on the graph of x plus y equals 6? Well, based on the graph, it doesn't look like that point would be on the graph of x plus y equals 6. So how do you know that the graph doesn't curve down at that point? How can you be sure? Well, you would have to see if -2 and 3/7 and 4 is a solution to x plus y equals 6, which it is not because -2 and 3/7 plus 4 is equal to 1 and 4/7, not 6. So therefore, that point is not a solution to the equation. So at this point, we can predict that the graph of this linear equation is a line. Does that mean that the graph of every linear equation is a line? Might there be some linear equations that have curves in them? For now, our only method of proving or disproving our prediction is plotting solutions on a coordinate plane. The more we learn about linear equations, the better we will be able to answer the questions we just asked. All right, so doing exercises 1 through 6. Example answers are given for the part of the tables, but your answers may be different because you might pick different points or numbers for x, either the x or the y. The graphs, however, will be the same as far as looking like they would create a line. So the points shown may be different than the points you determine. When you are done with exercises 1 through 6, go ahead and continue the video. All right, so let's see if at least your graphs look similar to what we have. So again, here are some examples of picking points. Again, not just picking whole numbers, but picking fractions. This is just one part or one half of the chart. But again, paying attention to showing your work as you substitute the values for x and you're solving for y, or substituting the values for y and solving for x, either way. But this is the amount of detail that you should have in your work. And here is what your graph should look like. It should be crossing the y-axis below 0 and should be moving from left to right in a downward slope. Answering the question, what shape does the graph look like it's taking? It appears to be the shape of a line. Again, cannot prove that in between these points there isn't a curve occurring here, but plotting these points makes it look, or gives us more evidence that it looks like it's going to be a line. All right, for number 2, again, some sample points to plot. And again, your graph of number 2 should look like a line moving from left to right in an upward fashion. So again, appears to be in the shape of a line. If you were to plot more points, it looks like it'd still be in the shape of a line. And again, it appears. The whole point, or a key phrase, is appearing to look like the shape of a line. Again, we haven't proven that it's a line. It's very, very difficult to prove that at this point because we would have to plot infinite amounts of points to prove that it is definitely a line. All right, so for number 5, Joey predicts this will look like the graph shown below. Do you agree? You should say no. And for number 6, your answers will vary. Can you come up with a graph that would not be a line? In this case, your x or y would have to have an exponent as one of the variables. All right. So all the graphs of linear equations we have done so far appear to take the shape of a line. Again, keyword being appear. And we can show whether or not a point is on the graph of an equation by checking to see if it is a solution to that equation. All right, we'll see you in class.